Andy, his space is for you.
Thank you, Santosh, and good morning, everybody. Thanks for the introduction. And yeah, I'll kick off with what I'm going to present today. So in customary fashion, can you see my screen?
Yes.
Brilliant.
Yes.
Okay, that's good. So yeah, so I thought what I present today is a particular issue, let's say, or an opportunity to profiteer from the fact that nowadays, of course, as we do lots of characterization of samples under real reaction conditions, we generate lots of data. But at the same time, you know, this is a problem, but it's an opportunity. So we're actually able to try and take advantage of some of this amount of data that we're generating to actually speed up the data processing side of things. So basically the technique I'm going to demonstrate today is this technique known as X-ray diffraction computed tomography. So that's what the XRD CT stands for there. We've got this kind of cartoon in the bottom that I'll run again in a minute. It seems to have moved on automatically. So basically what we are doing is we're collecting an image from a sample, you know, so it's a solid state material. And, but instead of trying to sort of effectively collect an image in black and white form, which is based on X-ray contrast, so how much the X-rays are absorbed, we're actually measuring the scattered pattern. So we're collecting a diffraction pattern on a 2D area detector that you can see here in the top left-hand corner. And so if I play the cartoon again, what you can see as we move a sample into an X-ray beam, that's the red line here, we collect these diffraction patterns. We build up a sinogram here. So you can see the rings there. So these are the bichiral rings that you typically get from powder diffraction data. And we're obviously doing lots of these kind of projections as they're known. So we're kind of scanning our beam through the sample and rotating it to build up a sinogram. And from that, we can build up an image. So what that means is that typically when you do an in situ experiment, you might collect one diffraction pattern from a particular point in the sample. We're kind of scanning through the sample, rotating it so we build up an image. So we're generating lots and lots of diffraction patterns from a sample. We're talking about thousands of diffraction patterns. And nowadays, X-ray beams at synchrotrons are so bright and detectors so sensitive that we actually generate diffraction patterns of the quality that you're seeing in the top right-hand corner here in a matter of milliseconds. So in fact, we're now limited actually by how quickly we can read off the data. It's not the data quality that limits essentially what we can get off from our experiments. So what we then need to do is, the reason we do that is that we know that materials, you know, by accident or by design, have heterogeneity in them. So ideally, sorry, these are Anthony Van Vakaros produced this for a presentation he gave the other day. He's obviously put timings on the slides. I've not realized until now. So I'm going to keep flicking back as it would turn up. Anyway, so essentially this is just a summary of what I just showed in that diagram. So what we want to do is we want to look for this heterogeneity because we want to put that into context of performance. So we have here effectively our sample. We're collecting our diffraction pattern on a detector here. There's the 2D images. We normally have to do some sort of pre-processing because sometimes we get these very sharp spots in the signal, which we need to just remove. So we effectively do this polar transformation here, and then we remove any of the strong intensities from that data. And then we basically collect or turn those data sets into one-dimensional diffraction patterns. So this is what we're familiar with as scientists who look at solid state chemistry evolution. We get these diffraction patterns that you can see here. And then effectively, we create the sinogram, which is diffraction patterns in the two-dimensional space. And then we effectively create these reconstructed images. And the key thing about actually taking the full diffraction pattern is that we can create an image about an aspect of the diffraction pattern. So for example, as you can see here, we've got different peaks. We can actually build up an image from those individual peaks. Essentially, it allows us to not second guess, let's say, what we're getting in terms of the diffraction data. We have actually got software that allows us to visualize the data. So essentially what you've got now playing in this diagram is just how it is that when we draw or drag a cursor over the image, we actually get change in the diffraction pattern. So we can actually look at the diffraction data on a pixel by pixel basis. And then of course, as you can see here, the cursor is being dragged through on the right-hand side here. And then you can see particular distributions that we can assign to a particular component in our diffraction signal. It's just to sort of show here, this is kind of diffraction data. So this is like a packed bed. So for those of you familiar with the type of experiments that typically we might do at a synchrotron, you've effectively got powder in a tube, where in this case, there's quite coarse grains. So you can see here, these are particles. They've got sizes of the order of a few microns to a few hundred microns. So we can look at the distribution of crystalline material on those. But the other thing is that this method is not limited to just looking at powders inside tubes. Here are data that we've collected recently from a AAA battery. So you can actually see, as we again drag the cursor through here, you can start to see the distribution of components like current collector or the cathode. So, as I mentioned before, in itself, it's an opportunity and a challenge. So as it turns out, the diffraction patterns that we collect are collected on a camera. A camera, of course, is producing image files. And as you know, typically with your standard camera, just same as what we're using here. It's not a standard camera, it's obviously an X-ray detector, but the image files are typically of the order of megabytes. We would be collecting several thousand diffraction patterns, and each of those patterns, or each of those projections, is typically a file size of a few megabytes. So if we're collecting many thousands within a particular experiment where we might collect as a function of time, we could be generating typically terabytes of data. And if we're in a particularly successful experimental run, spanning a number of days, looking at quite a few different sample environments, or carrying out a few separate experiments, you could quite easily generate terabytes of data. And actually it becomes a headache to handle that data, but over the course of the years, we've actually developed sort of software and capability that we can actually squeeze that data to make it more manageable. So instead of working with the raw image files, we turn them into the ASCII files. So we've basically got the one-dimensional diffraction patterns. And of course, they are, typically a few orders of magnitude smaller in size, but nonetheless, we've still got a lot of them. So we're still generating gigabytes of data. And in the end, what we want to actually do is analyze that data further. So we then run those through routines to analyze the data and then generate information that are still on the order of megabytes in size. So it's really a data handling problem that we've worked out how to kind of deal with to date, but it still provides us with a bit of a storage problem that I'll come to later. So here's just some examples of the value of why we do this. So for example, as I said before, materials by accident or by design often show some variability in composition, and this will affect performance. So for example, in this cross-section here, so here we have our, basically our setup, if you like. This is just a mock-up of what we've got, a tube with some content. We take a cross-section, and by this diffraction imaging technique, we can differentiate between two similar, compositionally similar materials. So these are polymorphs of silicon dioxide, cristobalite and tridymite, and we can differentiate those with these components here, which we know to be catalytically active. You pick out all those components quite easily. And of course, as I said before, we're typically doing these experiments as a function of time, or in this case, temperature and gas composition. So then you can actually sort of see what happens as we put the sample through its paces. So here at the top, we're changing the temperature, or we're changing the gas composition. And then we can sort of plot in two-dimensional space what happens to these various components. So one of the things that you can typically see here is that the cristobalite high, as it's known, is actually metastable with regard to tridymite. So you get one form of silicon dioxide converting into another. One of the things that's interesting is that you actually see that the outside of our container starts to actually react with the tungsten component, sorry, one of its own, to actually start to form a product that's actually undesired. So in fact, what we're seeing is that the component, the tungsten component in our system actually starts to react with the barium container, which is not good. These are kind of the reasons that we do these types of experiments. So we like to create these kind of nice real-time imaging files, or this is just illustrating how everything maps together to create the images. So we're able to separate out all of the components. So these hotspots here are that barium tungstate phase that I said was forming. And these are the grains within inside the container. So we can separate them all out now. One of the things that we can also do, because we've got the diffraction patterns in their entirety, is we can actually interrogate those diffraction patterns. So when you're looking at diffraction data nowadays to extract the most of it, you can fit those data sets. So you can basically identify all of the components present. So you get the phase distribution maps. But you can interrogate the peak widths as well to get crystallite size and the positions of those peak widths to basically determine what's known as lattice parameters. So we can actually, in a mixture of Xray and zirconia, actually determine how much intermixing there is of Xray and zirconia. So we can actually even identify solid solutions and even regions whereby you've got cerium-rich Xray zirconia or zirconia-rich Xray zirconia. And actually another thing, sorry, skipping ahead again there. So that's the sort of information that we're now looking to get from the diffraction computed tomography, because that really shows its value. So it's one thing to say that, yes, we've got different components in there, but in the end, as chemists, we want to understand structure-activity relationships, and subtle differences in the amount of Xray and zirconia will affect the performance of this material. Or, for example, the phase of the nickel. So in this case, we're looking at catalysts that convert methane into CO and hydrogen. So it's basically partial oxidation of methane. And there we know that we need to get a certain amount of metallic nickel in our system. So we're interested to understand where the nickel is and what form it's in. So in this case, it's nickel oxide, but we know as we change the conditions that will form nickel metal, and we can correlate that with activity. This is just to sort of illustrate that the capabilities that we have is not limited to diffraction. It can actually be used to interrogate a range of different sort of data sets. So here we have a setup that was built by Steve, designed and built by Steve Price, who's watching the seminar. And here we basically show that with one shot of X-rays, we can actually collect a diffraction pattern, a transmission signal, and also 90 degrees to this XRF or Zane's map. So we can actually pick out the different components that might not give you a diffraction signal. So we actually get a much more comprehensive characterization of our sample, but we still generate lots of data here. We still need, and we still have, and we actually have, data processing pipelines that allow you to reconstruct the maps here. So here, of course, we've got this diffraction maps that you've sort of seen earlier, but we can then compare that with this absorption contrast, which tells you where the particles are. And here the XRF contrast, which tells you what components are also present, but maybe in trace amounts. Of course, as we know with catalysis, sometimes small amounts of an additional component can have a big impact in performance. Of course, now with this type of setup, you can put all of that into context. Ideally, as you've seen, most of the data that I showed you previously is effectively a 2D cross-section. And of course, that's better than having a single point measurement, but it doesn't take into account the fact that we have a tube which has a height as well as a width. Sorry, Abraham, you just noticed you turned your microphone on. Am I about to be told that?
Yeah, now it's
okay. Just your voice sometimes drops, like you get away from the microphone.
Okay, sorry, yes. Yeah, I think this is probably my internet. I'm sorry, it has been a bit problematic all week. So yes, apologies. Yes, I guess it's just the world we live in now. Since the microphone should be always in the same place because I'm using a headset. Anyway, yes, I will push on. So as I mentioned, most of the time we're getting data from a 2D cross-section and not yet the samples show variability in height. So we have this challenge that it's not good enough to just measure a cross-section. We really need to get a volume. So that's what we've been doing in the last few years, taking advantage of the fact that the X-rays are bright, the detectors are sensitive, is to actually do a Z profile. So essentially doing lots of 2D cross-sections at different heights. And that's the result that I'm sort of showing you here. So we're just looking at, for example, as we change the sample environment and the fate of the nickel oxide here, as you can see, as we change the gas environment, evolves with temperature, reaction conditions, and time. So essentially nickel oxide in our catalyst particle here is present at the beginning. As we start to heat this up in a helium atmosphere, we start to see that there's reduction taking place. And as we switch then to hydrogen, you can sort of see that there's this gradient. So essentially here we are collecting lots of 2D cross sections as a function of time. So essentially we're scanning from bottom to top. So what's happening here is that as we begin the scan and passing hydrogen over the catalyst, we actually still see some nickel oxide, but as we profile through the bed, we see that the nickel oxide is reduced to nickel metal. So you see an inverse distribution of nickel metal with respect to nickel oxide in this image here, sorry. So here we have nickel oxide at the bottom and nickel metal at the top. And that just tells you that as we're measuring up through the sample with time, basically the nickel oxide is being reduced. We also pick out these other phases forming. As I said, that's the sensitivity of the technique. And then of course, we can also extract particle size information. But as you can imagine, if we're getting what we call 5-dimensional imaging, so that's the 3 spatial dimensions as a function of time, but each pixel in that data set contains a full diffraction pattern. So there we define that as chemical information. I know within FINDOM we have a bit of a discussion as to whether or not that extra dimension is the chemical environment surrounding the catalyst. So it could even be 6-dimensional tomography, but I don't know. I think, at least for me, the 5th dimension is the fact that each pixel in that image contains a full diffraction pattern. But in order to get that data set, essentially we're collecting over 1 million diffraction patterns. So you have this data processing problem that we have to handle it. There's often artifacts in the data. So I mentioned beforehand, we have a way to kind of remove some of those, but there's other problems as well. That when you have a very large sample, you have basically this, what's called parallax problem. So that's basically simply that diffraction is happening at different parts of the detector from the same signal. So essentially you might be seeing the container scattering from the X-ray beam from the front of the sample and at the back of the sample. So it gives a broadening in the detector, and it gives you basically a broadening of the signal. So if you've got to basically apply all these corrections, then you're going to have a problem in getting to the analysis side of things. So that's where we've tried to apply machine learning methods. So this is just basically the outline of the architecture, PQNet, which is basically called phase quantification net. Basically, I'm not an expert in machine learning, so all I could really say is that this approach is basically picking out components of the image and then trying to basically apply particular kind of thresholds to those images in a way that in the end you effectively cover all the data that you've got, such that you've taught the machine to look at the data that you've got, and then you can basically give it a similar set of data and ask it to interpret it. So you're basically training the machine or training the software to do an analysis on data that's similar. So effectively, this is the architecture around that it does, how it does this. And effectively, we can extract, for example, the phase quantification aspect is scale factor. So we can say how much crystallite size, how wide are the peaks, and what does that relate to in particle size, and then the lattice parameters. So essentially, the good thing about this method is that it automates the process, as you'll see in a minute, saving you a lot of time. I mean, in itself, this has been quite an endeavor. So we've had a PhD student working with us from UCL. Obviously, I'm UCL, and by us there, I mean working with FINDOM Limited, to kind of tackle some of the issues with, effectively multiple phases, poor data quality, and some variation in the database, which makes interrogation of these data sets difficult. It makes it difficult from an analyst perspective, but also it's something that the machine learning has to also consider dealing with. And essentially what I'm going to show you now is the outputs from that. So essentially what we've got here is what we call the ground truth, which is something that we've actually extracted from the analysis using Rietveld method, so applied in what's known as a parametric way. It can also be done sequentially. So basically you take your 10,000 data sets or so and you just tell software, conventional software, just continuously refine the data until you've done all the 10,000 diffraction patterns. And essentially, this is what we extract from that. And then this is essentially what the machine learning has also managed to kind of extract. So what you can see here is there's the data that we've analyzed in the conventional way. This is the machine learning approach, the PQNet. And this is the difference between those data sets. And as you can see, particularly if you compare those two images, okay, you've got to bear in mind the scaling is the same. So that any difference there is actually, you know, an order of magnitude lower. So it's basically saying that we've actually captured the salient points of this real sample in the machine learning method. Right, let's fit there, but anyway. And the same with the lattice parameter. So again, if you look here, the scaling here tells you that the analysis of the nickel lattice parameter, so it's one of the components, from the machine learning approach is actually very, very reliable. And it's not just, for example, nickel metal. We've actually applied it across all of those components in this multi-component system. And as you can see here, the errors are very, very small indeed. The alumina has the biggest error because it's the least crystalline component in our system. And this is just to sort of show you that, in fact, the data that the PQNet is actually simulating is actually really quite complex. So essentially here you've got two components, the fit against the real data and the fit against the PQNet data. And as you can see here, the fact is that you've got all of these, let's say, wiggles in the data set suggests actually that you've got a very, very robust method of screening a large volume of data. And this is where the value comes in. So essentially for us to analyze several thousand data sets, so 20,000 diffraction patterns, or as you can see here, it's a scaling problem. So the more that you're analyzing, the longer it's going to take. But the PQNet approach is actually enabling us to kind of process these data sets in a much more efficient way. So this actually allows, for example, real-time data processing. So when you're doing an experiment at a synchrotron, you're still doing the data analysis blind, where effectively you're doing the experiment blind. So you do the measurements under reaction conditions, and you hope really at the end that if you sample one or two data points during the experiment, that actually that's representative of the system as a whole. But now, in principle, with this capability, you could actually look at real-time reconstruction of the data so you can drive your experiment. So that's basically what I wanted to show today. But I suppose one of the key things for this workshop was perhaps how, well, I guess some learnings and opportunities. So one of the things that I think is quite interesting as the Catalysis Hub is that, you know, potentially as a network of researchers, we're generating a hell of a lot of data. And of course, now we're starting to think about how we can profiteer. So, I mean, of course, there is this challenge that I think is illustrated in what I've shown today, in that most of the time, the data that we're generating, the raw data, it's difficult to store and profiteer from. But I think with diffraction data, that's really quite critical. And I'll tell you why. Hopefully some of you may sign up to Chemistry World. So that's a Royal Society of Chemistry kind of trade magazine. Sure you're all familiar with that. And actually this month, I'm quoted in one of the features that they actually highlight on some recent research. And this was all to do with analysis of diffraction data. And the article that the Chemistry World is featuring is about an analysis of data where experts in diffraction were able to identify that the solution provided by computers was not correct. And that mainly is because computers, when you're doing structural solution for diffraction data, really only look at the strong reflections. When in fact, if you looked at the raw data, you'd find there's some weak reflections in diffraction data, and those weak reflections shouldn't be ignored because they provide or help you understand what the real solution to the problem is. And I think that's a key thing with us is that, you know, for example, with PQNet, it's taking the raw data. So of course it's trained obviously based on what we're essentially putting in as far as solutions are concerned. But it means that essentially, if we're looking at all the data, we can even tell it, look, okay, sometimes you need to look at the weak reflections in order to come up with a correct solution. So essentially there's an opportunity there when you're using raw data, but obviously in our case, our raw data are terabytes in size. So how do we basically benefit from the raw data in a way that, you know, manages the kind of the data size, let's say. With the process data, we try to make as much of this data available as possible, but now this problem is that it's not coherently stored, it's not stored in the same place. And then, of course, there is this issue as well of how do you put it in a way that, how do you store it and make it available in a way that people can make best use of it? So these are some of the issues that I highlight here. But just to conclude, I think, you know, within this situation, we do, I think, have a great opportunity to, you know, speed up our processing pipeline. A key thing that I showed today is that we're using all the data now rather than just some of it. So that's one of the problems I still think we face as a community collecting time or space resolved data. We might only look at 1 or 2 representative signals from our data, whereas, you know, potentially we could be using a lot more of it. I'm sure for this community, I'm preaching here to the converted, but I think that some of the points I'm making here are still issues that we need to overcome. Finally, this is just to thank a lot of people who helped, well, basically put together this presentation, but actually also in getting all the data that I showed today. And finally, thanks to you all for your attention. That's me finished, Santosh.
Thank you, Andy.